Ancient stories from around the world bear witness to sinister lakes. Killer waters that bring death to those who look at them. For years, these were just legends. But now, scientists are discovering that some lakes are deadly. There are more than 100 crater lakes worldwide. Some threaten millions. How does a calm lake become a killer? If there was a list of nature's greatest hazards, few would put lakes near the top. Some have been revered for centuries as sacred places. Others have become tourist attractions. Many are barely known. But they all have one thing in common. They're all in volcanic regions. Some are even inside the craters of active volcanoes. And now, experts have uncovered a terrifying series of dangers. The wake-up call came in Cameroon on the west coast of Central Africa. This is Lake Nyos. It sits in the crater of a dormant volcano. In 1986, more than 10,000 people lived in the valleys that surrounded the lake. Then, without warning, tragedy struck.
On August 21st in the afternoon, everything was fine. Then around 9 o'clock in the evening, we heard a noise like thunder coming out of the lake. I saw a light reflecting from the lake. I went outside and there was a smell like rotten eggs. I've never smelt that kind of smell.
The cattle herders who live on the hills above tell of a wave over 80 feet high and the color of the lake turning brilliant orange.
My children were crying. All around, my people were dying.
Al-Haji lost 31 relatives over the course of that terrifying night. At least 1,700 people died. Within days, experts arrived to investigate, including lake expert or limnologist Dr. George Kling. A year earlier, Kling had surveyed Lake Nyos and found nothing unusual.
The lake was changed completely from when I'd seen it a year ago. It looked like a giant tidal wave or hurricane had gone through and just moved away all the vegetation and changed the color of the lake.
Survivors' stories of feeling warm and the smell of rotten eggs pointed investigators in one direction.
Everyone thought that this was just a volcanic explosion.
But when they test the vegetation for traces of hydrogen sulfide, the volcanic gas that smells of rotten eggs, they found nothing. There was no evidence of temperature change in the lake either. And no one reported witnessing an eruption. But something had turned the lake bright orange. Over 1,700 people were dead. Scientists need to find out why. A clue to what happened here is almost 8,000 miles away. Oregon. Crater Lake has been a national park since 1902. The lake covers over 20 square miles and contains 5 trillion gallons of water. It's as deep as 1,949 feet, making it the 7th deepest lake in the entire world. Drop the Empire State Building in the lake, and it would disappear beneath the surface. There have been no mysterious deaths at Crater Lake, but scientists still study its every movement. And what they find here helps explain the terrifying suddenness of the Nias tragedy. Today, Mark Botenica of the National Park Service is out on the lake taking measurements. He's the latest in a line of Crater Lake researchers that stretches back over 100 years.
And one thing you need to realize is that you are inside a volcano looking out. And the entire violent history and evolution of the mountain is detailed and laid out before you in the geology and the landscape around the caldera.
To understand how this lake works and what light it sheds on the Nias mystery, we need to go back 7,700 years. At that time, the landscape here was dominated by the 12,000 feet high stratovolcano Mount Mazama. Then, the volcano violently erupted. The eruption was 42 times the size of Mount St. Helens in 1980, and the largest ever witnessed on the American continent. 12 cubic miles of molten rock poured out from the volcano. Ash deposits over more than 1 million square miles. Native American legends tell of the day turning to darkness for almost a week. The eruption was so powerful that the top 5,000 feet of the volcano collapsed, forming a crater 6 miles across. Nearly 8,000 years later, rainfall and snow have accumulated to form Crater Lake. Today, the lake appears calm. But Botenica knows that the molten rock that provides the power for volcanic eruptions still runs 8 miles beneath it. This landscape can undergo geological upheavals without any visible signs at the surface, because the lake conceals them. He discovers this in 1988 when he becomes the first researcher ever to examine the lake's deepest point in person.
It's about a 20 to 30 minute commute to the bottom of the Crater Lake in the submarine. And as you're lowered, you're just engulfed in an intense blue. Slowly the blue becomes a little blue-black, and eventually you're engulfed in near total darkness at the bottom of the lake.
The submarine's floodlights reveal a landscape jutted with sharp rock. It's lava that cooled as it came into contact with water. Using state-of-the-art sonar mapping, Botenica creates the clearest picture ever of the lake floor. He also finds something unexpected. 2 pools surrounded by colonies of golden-colored bacteria. It is unusual for colonies of bacteria to live in total darkness, away from the energy of the sun. Botenica realizes that the colonies must be getting the energy necessary to thrive from the pools. To test this, he takes temperature readings and discovers the pools are several degrees warmer than the surrounding lake water. Then he analyzes the water's composition. He discovers the saline content is 10 times higher. And it contains the gas carbon dioxide. They're hot springs. Their heat and gas originate miles down where the magma runs beneath. 1,000 tons of carbon dioxide enters the lake every year. It's a clue that CO2 might be contained in other crater lakes, like Lake Nyos. Could carbon dioxide be the killer gas that brought death to Cameroon? Few people would put lakes at the top of their list of natural hazards. But lakes and volcanic areas can contain dangerous gas. And in 2006, volcanic gas tragically killed 3 people at Mammoth Lakes, California. This resort town sits within the crater of a giant active volcano, the Long Valley Caldera. Visitors can see volcanic gases venting around the area. The most common are water vapor, carbon dioxide, and sulfur dioxide. These gases begin their journey over 5 miles down. The weight of the rock above creates a pressure at least 2,000 times greater than that at the surface. This pressure traps gases in the magma. But as the magma rises, the weight of the rock above decreases and the pressure drops. Volcanic gases escape from the magma. They percolate through the Earth's crust and into the atmosphere. Professional geologist Charles Watson investigates the risks at Horseshoe Lake, close to Mammoth's main resort.
There's this quiet, silent killer that's lurking about in the trees along the lake's edge.
In the early 1990s, trees began to die in the area north of the lake. The cause? High concentrations of carbon dioxide. Scientists have discovered that around 100 tons of the gas escapes around Horseshoe Lake every day, raising the level of carbon dioxide in the soil up to 95 times normal levels. A simple test at the lakeside shows what this really means.
Carbon dioxide's heavier than air. So what we've done is we've dug a hole, and the carbon dioxide's going to fill that up and displace the oxygen out and extinguish this butane lighter.
Fire needs oxygen to burn. Starved of this, the flame dies.
It won't even relight.
High concentrations of carbon dioxide can kill a butane flame in seconds, and it can have a deadly effect on humans. The usual concentration of carbon dioxide in air is only 0.035%. At a concentration level of around 1%, it causes dizziness, headaches, and hallucinations. Above 17%, unconsciousness and death happens in a matter of seconds. At Mammoth Lakes, wind usually disperses the carbon dioxide safely. But in 2006, investigators confirmed that a lethally high concentration of the gas killed 3 ski patrollers who fell into a snow cave on Mammoth Mountain. And there was no volcanic eruption. Did carbon dioxide also kill over 1,700 people at Lake Nyos in 1986? When investigators arrived at Lake Nyos, they found no evidence of a volcanic eruption. But they did discover that carbon dioxide was feeding into the lake, but only in small amounts. Autopsies over the following weeks reveal carbon dioxide as the main cause of death. But there's a mystery. Lake Nyos produces less than 15 tons of CO2 per day, compared to the more than 100 tons daily around Horseshoe Lake. So how could it have killed so many people as far as 16 miles away? In 1986, the Nyos Valley, Cameroon. More than 1,700 people die in the valleys around Lake Nyos, asphyxiated by carbon dioxide. Scientists estimate this would have required as much as 1.75 million tons of the gas. Until now, these quantities have only been recorded as a result of volcanic eruptions. Yet there was no eruption at Nyos. University of Michigan limnologist Dr. George Kling has concluded that this huge volume of carbon dioxide must somehow have been trapped in the waters of the lake.
It's kind of strange to think that a lake could hold that much CO2.
Magma beneath Nyos releases carbon dioxide, which travels up through the Earth's crust to the bed of the lake. Scientists estimate that about 5,000 tons of the gas escapes into the lake every year. But what is it about this particular lake that means such a large volume of carbon dioxide can accumulate? Lake Nyos is a deep lake containing 47 billion gallons of water. At points, it's over 680 feet deep. The weight of the water above and the pressure increase with depth. The pressure at the bottom is 21 times more than at the surface. And high levels of carbon dioxide will dissolve in fluids under high pressure. Take a bottle of champagne. Champagne's fizz is carbon dioxide. In the bottle, it's forced into the liquid under high pressure, which is maintained by the cork. But pop the cork, the pressure drops. Less dissolved CO2 can now be trapped, and it returns to gas form and escapes the liquid in a mass of bubbles. At Nyos, the weight of the water above does the job of the cork.
The weight of that water is keeping the gas dissolved in the bottom waters, and it can build up to tremendous concentrations.
The deepest water of Lake Nyos has the capacity to hold nearly 2 million tons of dissolved CO2. But it would take over 300 years for that amount to accumulate. However, in most crater lakes, carbon dioxide dissipates on a yearly basis. During summer, air temperatures keep the surface water warmer than the lower water. In the same way that heated air rises to float balloons, warmer water will ascend above denser, colder water. But in winter, the water at the top cools more quickly than the water below. As it cools, it becomes denser than the deeper water and sinks, forcing the lower water to circulate and rise nearer the surface. When the deepest water rises, the pressure drops and dissolved carbon dioxide escapes, preventing a buildup from occurring over a period of centuries. But at Nyos, there are no colder seasons. In this equatorial region, consistent heat from the sun throughout the year ensures the upper waters always remain warmer and lighter. Over time, the lake develops distinct layers of different densities of water. This layer cake structure is called stratification. It means that carbon dioxide can build up in the deepest water over centuries. A team of scientists from the BP Institute at Cambridge University in Britain investigate how carbon dioxide builds up in the stratified lake. Red dot models the behavior of the dissolved carbon dioxide at Lake Nyos. It accumulates in the denser lower layer of the water in the tank, unable to break through to the upper layer. But just as the cork needs to be released to free the gas in the champagne, something must have happened at Lake Nyos on August 21, 1986, to discharge over 1 million tons of carbon dioxide into the atmosphere. A collapse on one of the steep cliffs of the volcanic crater is the likely trigger for this tragedy. It crashes into the lake, disturbing the stratified water. It pushes the CO2-rich water towards the surface, where it explodes as it releases the gas. A cloud of carbon dioxide fills the crater, then rolls over the rim. The gas clings to the ground. It's 1.5 times heavier than air and flows down the mountainside like water in a flood, searching for the lowest areas. Most villagers in the valley don't stand a chance. Today, 12,000 people are still displaced from their homes. A system of degassing pipes installed in 2001 safely siphons carbon dioxide from the lake. They're slowly decreasing gas levels, but Nyos still contains more CO2 today than escaped in 1986. Was Nyos a one-time event? Or can other volcanic lakes accumulate enough carbon dioxide to become equally dangerous? There are 3 essential elements: a way in for the dissolved carbon dioxide, a depth of at least 160 feet to create enough pressure, and an equatorial location to prevent dissolved gases escaping during the colder seasons. Combined, these 3 factors discount most volcanic lakes. But one location has got the experts worried. Lake Kivu, on the border of the Democratic Republic of Congo and Rwanda, is 2,000 times larger than Nyos and has 1,000 times more dissolved carbon dioxide. It also lies close to a nearby active volcano, and some scientists believe that an eruption here could trigger a catastrophic release of carbon dioxide from the lake, threatening the 2 million people who live on its shores. A rare combination of circumstances makes volcanic lakes like Nyos and Kivu deadly. But the lethal combination of a volcanic system and water is not confined to equatorial Africa. Much closer, more than 150,000 people face a different but equally catastrophic threat from a crater lake. The combination of lakes and subterranean volcanic networks can be devastating. And experts have identified a major hazard from the interaction of water with a volcanic system right in the U.S. Washington State. Mount Rainier stands less than 70 miles to the southeast of Seattle. It's one of the Cascade Range of volcanoes, which includes Mount St. Helens, and extends for 700 miles in western North America. At 14,410 feet high, its summit is often hidden high above the clouds. To the naked eye, it doesn't appear to have a crater lake. But hidden amongst the 26 glaciers on Rainier is a tiny crater lake measuring 80 feet by 60 feet. Ice caverns carved by rising heat from the volcano entomb the lake. Volcanic gas is the reason why this meltwater lake and the frozen water in the crater above it threatens the lives of more than 100,000 people. Sulfur dioxide is the gas that poses the threat here. To find out why, we need to go inside the lab. Take some sulfur, burn it with oxygen, and you get sulfur dioxide. Let that sulfur dioxide combine with water. We end up with sulfuric acid. Drop some volcanic rock into a test tube of our acid. A few tiny bubbles form around it. In fact, the acid reacts with the rock, introducing new elements that change the rock's chemical composition. Drop a piece of rock into stronger acid, and the process is speeded up, leaving only sediment in the bottom of the test tube. Rainier is the real-life version of this experiment. Sulfur dioxide escapes from the magma chamber 5 to 6 miles below and rises throughout the volcano. It meets water. They combine and form the acid. Geologist Kevin Scott has spent nearly 30 years studying the impact of acid water on Mount Rainier.
As this material percolates throughout the volcano, flowing through cracks and crevices and fault zones, it acts to alter the hard volcanic rock.
Volcanic rock forms when magma or lava cools. It's a strong rock, not easily broken or crushed. But over centuries, the acid alters it. It becomes so weak it crumbles in the hand. This goes on at every volcano where gas and water are present. But Rainier is particularly dangerous. It's as much as 1 million years old. As one of the oldest Cascade volcanoes, acid has permeated, chemically changed, and weakened the rock at Rainier for much longer than its neighbors, like 50,000-year-old Mount St. Helens. Rainier's changed rock is structurally weak, water-saturated, and could give way at any time. If it collapses from the top of the volcano, it can transform into a muddy slurry that flows down the mountainside.
The way to picture one of these mud flows is to think of flowing concrete.
They're called lahars. The 1980 eruption at Mount St. Helens, only 50 miles from Rainier, demonstrated their destructive power. The upper 1,312 feet of the volcano crashed down the mountain in the largest landslide in recorded history. Within minutes, melted snow and ice added to the debris, creating numerous lahars. They were twice as dense as water and traveled at up to 45 miles an hour. The largest traveled almost 70 miles, wiping out nearly 200 homes in its path.
They have really taken far more lives over the last several decades than volcanic eruptions.
And a lahar at Rainier poses an even greater threat. Not only is there hugely weakened rock that could collapse at any time, but there's also a vast amount of water. Rainier supports more than a cubic mile of glacial snow and ice, 5 times more than all of the other Cascade Range volcanoes combined. A rock collapse could not only breach the crater lake, but also bring down some of the frozen water from above it. It might only take a small amount of this to create a devastating lahar. Unlike Mount St. Helens, there's no written record of large lahars at Rainier. But Scott scours the landscape for evidence of events that might have happened before records began. It helps him figure out how threatening the mountain is.
What geologists do to try to assess the volcanic risk is work out the history of the volcano. We like to talk about tracking an animal. If we see the tracks of a polar bear in the snow, for example, we know we're eventually going to come on a polar bear.
If Rainier has experienced large lahars in the past, then they're likely to occur again in the future. On the lower slopes of Rainier, Scott finds trees buried under a layer of mud and rock. As he spreads his investigation further away from the mountain and into the surrounding valleys, he makes a shocking discovery.
This 25-ton piece of rock was originally part of the top of Mount Rainier.
A lahar carried it 30 miles, and it now sits in the back of this suburban garden in the city of Orting. 500 years ago, a lahar buried the Puyallup River Valley, and now the entire city is built on top of it. There's evidence of 55 lahars. They range in length from a few miles to 70 miles. The biggest had a volume of more than 2/3 of a cubic mile, the equivalent of the contents of 1.2 million Olympic-sized swimming pools. At least 15 of them surged through Puyallup Valley. The largest traveled as far as today's ports of Tacoma and Seattle, and devastated areas that over 150,000 people now inhabit. Lahars on this scale have happened every 500 to 1,000 years. So the question for the residents of Orting appears not to be if, but when another lahar will strike the valley. A lack of eruptive material in previous lahar deposits reveals an ominous fact.
We know they can occur here at Mount Rainier without any eruptive activity.
Without any warning, part of the mountain could collapse. Acoustic monitors on Rainier will only sound the alarm once the lahar has begun. The United States Geological Survey calculates that the people of Orting will have only 40 minutes to evacuate. At its worst, millions of tons of rock, ice, and debris traveling at over 50 miles an hour could devastate valleys all the way to Puget Sound, more than 60 miles away. It's volcanic gases interacting with water which creates the dangers at these lakes. But gas is not the only way a volcanic system can make a lake deadly. In 2003, research revealed a hazard that threatens America's first and oldest national park, Yellowstone. This time, gas isn't the culprit. Lakes in volcanic areas may look calm at the surface. But in fact, They are the visible part of a plumbing system that can stretch many miles underground. It's the volcano beneath that drives this system. In 2003, geologists in America's oldest national park revealed a new mechanism for a crater lake to become a killer. Wyoming. This is Yellowstone Lake. At 136 square miles, it's the largest high-altitude lake in North America. It sits in the southeast corner of the park and appears the perfect picture of serenity. But over 10,000 geothermal features at Yellowstone make it obvious that this is an active volcanic area. Dr. Lisa Morgan works for the United States Geological Survey. She has discovered exactly how the volcano beneath can turn this placid lake into a deadly hazard. In 1999, Morgan and her colleagues used state-of-the-art multi-beam sonar imaging to create the most comprehensive mapping of the lake's floor ever done.
We made dozens of discoveries and really changed the thinking from what was known prior to our mapping.
Morgan finds a dome that rises 100 feet from the lake floor and stretches the length of over 5 football fields. And she thinks the key to understanding how the dome formed is underground heat. Beneath Yellowstone is a vast magma chamber. And in some parts of the park, it may be only 3 miles below the surface. The magma stored in the chamber could be hotter than 1,400 degrees Fahrenheit. And the heat rises, warming groundwater all over the park, including under Yellowstone Lake. It can heat the water beneath the lake bed to up to 460 degrees Fahrenheit. As the temperature increases, the water expands and pressure builds. Morgan is certain water expansion and pressure increase causes the dome on the lake floor. The park's famous geysers are the clearest product of high-pressure groundwater at Yellowstone. There are more than 100 active geysers at Yellowstone. The king of them all, Old Faithful. It erupts water and steam at temperatures as high as 350 degrees Fahrenheit, up to 180 feet into the air. And it does this on average every 74 minutes. A geyser works in the same way as a whistling kettle. A source beneath heats the trapped water. A camping stove provides the heat for the kettle, while the magma chamber heats the groundwater. The water expands and pressure increases as the temperature rises. Finally, it forces its way out through any available escape. Steam rushes out through the whistle in the kettle. A higher pressure ejects water from the geyser. The water erupts out until the pressure is dissipated. But there's an essential difference between Old Faithful and the dome on the lake floor.
The thing with a geyser is that there's an escape valve. There's an escape area that the water is able to come out of.
The domes appear to have no release valve. Morgan fears that if the pressure becomes too great, it could explode up through Yellowstone Lake in what geologists call a hydrothermal explosion. Morgan searched the park to see if it's happened before. A volcanic eruption leaves deposits, including cooled lava. But a hydrothermal explosion leaves different evidence. The hot water dissolves minerals, which then percolate and react with, or hydrothermally alter, the surrounding rocks and clay. Finally, she discovers what she was looking for. She found layers of clay sediment, its color hydrothermally changed by zeolite minerals flowing through it. Nearby, she found rocks with veins of silica minerals, another sign of hydrothermal alteration. In total, she uncovered evidence of 25 major hydrothermal explosions in the last 20,000 years. By comparison, there have only been 3 giant eruptions at Yellowstone in over 2 million years. Now she goes back to the sonar mapping of Yellowstone Lake's floor. There's a crater 1.5 miles across under Mary Bay at the north end of the lake. And sediment samples show hydrothermal change. 13,800 years ago, the largest hydrothermal explosion ever documented created this crater. 100 million gallons of boiling water exploded into the atmosphere. A huge tidal wave swept across the lake. Rock and mud covered an area of 10 square miles. So can Yellowstone expect another massive explosion soon? Morgan looks at all the evidence. 18,000 years, 25 explosions. That's one about every 700 years. And the last big one was nearly 3,000 years ago. So it appears that another major explosion is long overdue. But can we predict when? Morgan believes that it's not simply pressure that causes the groundwater to explode. It needs something to set it off.
It's happy just going along being a restricted system until you get something that triggers a pressure drop in the system.
At Mary Bay 14,000 years ago, that trigger was an earthquake. The weight of the lake water had applied enough pressure to stop an explosion. But the earthquake shook the ground beneath the lake and made the water recede from Mary Bay. Less water meant less pressure, just like removing the cork. The trapped groundwater exploded. Thousands of small earthquakes rattle the Yellowstone region each year. Nobody knows exactly when another earthquake will trigger a new hydrothermal explosion at Yellowstone, or if the only warning will be the earthquake itself, just seconds before the explosion. But it's happened many times before, and it will happen again. The terrible death toll at Lake Nyassa in 1986 was a grim warning of the dangers from the interaction between volcanic systems and large bodies of water. More recent work at Mount Rainier and Yellowstone exposed further hazards hidden beneath the sinister depths of crater lakes across the world. Mankind has honored and feared the twin elements of fire and water since ancient times. But it is only now that we are starting to truly understand the threat that this combination poses deep below the calm surface of the Killer Lakes.